Hi, this is a presentation for the NASA Micro-G Next Quick Release Tool Design Challenge, showcasing our design, the OTRA, or Omnidirectional Tool Retention Apparatus, presented by the Blazars, Andrew Davison, Colton Mateka, Trevor Smith, and Miguel De Leon. Today's presentation contents are split into 6 sections. Section 1, Project Goals. Section 2, Criteria and Constraints. Section 3, Technical Background. Section 4, Concept Evaluation. Section 5, Modeling and Analysis. And Section 6, our plans for Semester 2. And with that, we can move on to Section 1, Project Goals, presented by Miguel De Leon.
The team's project goals are to design a two-piece quick-release mechanism for NASA's spacewalk at the Moon in 2024, and to demonstrate the functionality of our 3D prototype, and if our design is chosen, we are to manufacture the real prototype and test it at the Neutral Buoyancy Lab. Now for the criteria and constraints. One major constraint that we have is the 4-hole bolt pattern that we must follow in order for the design to work. It should be able to hold 15 pounds of weight, and it should require minimum force to detach the tool from the belt. All parts should weigh less than 2 pounds, and it should fit within a volume of 4x4x3, and lunar dust shall not impede the functionality of the device. The device should be easy to use, and it should be operable outside the line of sight and with one hand by the astronaut. It should be operable using a large and bulky spacesuit glove. The design should not have sharp edges or holes. The device should be either made out of aluminum 6061, aluminum 7075, stainless steel, or Teflon. Now for the technical background, Trevor Smith.
The current system uses bayonet probes attached to tools that are inserted and locked in place inside an enclosed unit. A redesign is desired for surface operations, as this design is non-dust tolerant, which is a chief concern for terrestrial expeditions. Regarding lunar dust, there is currently no standard definition of size, but the term loosely describes regolith particles up to 100 microns, but they are typically around 20. As referenced, this fine simulant from NASA has an average size of 27 microns, which is roughly 1,000th of an inch. Dust contains abrasive angular silica oxide particles and is electrostatically charged, causing it to cling to everything, which creates the risk of wear and tear on equipment, as well as respiratory health risks if large amounts are unintentionally brought into a controlled habitat. Out of the allowable materials, we focus mainly on aluminum and stainless steel options, with a focus on resistance to wear and mechanical properties at low temperatures, using Brinell hardness number as an indicator of wear resistance. Ultimately, 400 stainless was disregarded because of its magnetic properties and brittle behavior in low temperatures. Our selection narrowed down to 316 stainless and aluminum, with an edge given to 316 for its excellent properties at low temperatures and superior corrosion resistance, which may be useful for future Mars exploration and extensive EVA hours. At this stage, we are considering moving forward with 316 stainless as our material of choice, and confidence that replacements will not have to be launched into space. And now, Colton Mateka will cover our concept evaluation.
So in total, we actually generated 6 concepts, and we were able to narrow this down to 3 right away, just by looking at their ability to meet the product requirements set forth by Micro-G. We're only going to look at the top 3 today, so we're going to start with number 1. This one was basically a metal piece pushed between 2 rods. The rods would deflect out of the way. Once the metal piece was all the way through, the rods would deflect back in, sort of locking the metal piece between the rods. This one was very compact. It was light. We had no concerns with it functioning in a dust environment, and it was very nice that you could orient the tool in any way, 360 degrees, in order to get the pieces to align. We were a little bit concerned with its ability to hold 15 pounds and to remain interfaced. Concept 2 didn't really have this problem. It was very durable. It was strong. It required a minimal removal force because you're basically just trying to overcome the weight of the tool. And when the pieces were interfaced, there was no rotation of the tool. The concerns with this one had to do with dust. We were afraid that it might impede the operation of the ball spring plunger, and the ability to align these pieces up out of the line of sight seemed a little bit difficult. Looking at concept 3, it was very simple. It was basically a quip. This one also had very strong attributes for operating in a dust environment, as well as not rotating once it was interfaced. However, it seemed a little bit difficult to design the clip to be able to support 15 pounds, but also just require a minimal removal force to separate the pieces. There are also some pinch points, so safety became a concern with this one. So this is the actual concept decision matrix that we used to compare these 3 concepts. We actually decided to assign weights to each of the criteria, where a lower value for a weight indicated that it was less of a priority. So this had to do with things that were more related to comfort when using the product, whereas a value of 2 were constraints indicated by micro G, functionality of the product, safety, a big concern in any design, as well as the design considerations that NASA iterates on and their procedures for EVA operations. We were able to come to the conclusion that concept 2 was the best concept to move forward with, and Andrew Davison will talk a little bit more of how that design developed as we went along.
So for the modeling and analysis, we created a 3D model based on concept 2 and iterated on it several times until we arrived at the OTRA. Displayed here is a CAD render of the current prototype for the belt piece, along with its extreme dimensions. Now, the tool piece. As for the functionality and design features of the OTRA, the belt piece consists of a male track system with a cutout on the bottom to prevent dust buildup and a ball spring plunger for tool retention. The tool piece features a disc-like shape that slides into the track of the belt piece. Once slid into the belt piece, a detent in the center of the disc engages the ball spring plunger and locks the tool in place. Note that the disc shape allows for the tool to be in any orientation while being slid into the belt piece. You can see these features outlined in the 2 isometric diagrams displayed here. Here is a visualization of the tool piece sliding into the belt piece for tool retention. The OTRA has one pre-built vendor component, the ball spring plunger. The plunger we selected is a friction-bearing ball spring plunger with a hex head so that it could be easily installed or removed. This plunger is well suited for our application because the friction bearing effectively seals out lunar dust with its very fine clearance of only 1/1000th of an inch. The JSC lunar simulant has an individual particle size just larger than 1/1000th of an inch, so this plunger should not be affected by dust whatsoever. The side force is defined as the amount of force required to engage or disengage a ball plunger from its slot or detent, and is effectively the force the astronaut will have to apply to remove the tool from the OTRA. Using the simple equation we see here, along with the manufacturer listed value for FE, we obtained a side force of 3.23 pounds, which is enough to make tool removal easy, but still deliberate. And with that, we can proceed to Section 6, our plans for Semester 2, presented by Colton Mateka.
So the second phase of our project is actually going to take place during the spring semester. This runs from about the middle of January towards the end of May for us. The main things that we're going to be looking to accomplish during this time are manufacturing and testing of the prototype. For our product, we chose to have it machined via a CNC mill, and we'll perform any of the finishing operations once this is complete. That may include deburring or grinding. We'll also tap the hole for the ball spring plunger and install the ball spring plunger. After all this is completed, we'll move on to testing, where we'll develop procedures for the experiments that we're going to perform. We'll conduct those tests, which will focus on loading capabilities of the pieces, as well as the force required to interface or separate the pieces. Once we've completed all those tests, we'll gather the data, analyze it, and put it together in a report. It may be worth noting that testing could continue at the Neutral Buoyancy Lab, where we'd be able to look a little bit more in depth as to how this product is going to operate in a lunar environment, as well as minimal gravity. We'd like to conclude by saying thank you for your time and attention today, and we look forward to any questions that you may have.